Okay, let's start. So this is week number 6 of our course on probability and stat, which means we are officially ending our first half of the course. Are you able to see my screen? Okay, then let's start with highlights as usual. So this week was about functions of random variables, which means we have a list of random variables x1, x2 up to xn, and then we take it through some functions g1, g2, etc. And we go to different variables y1, y2 up to yn or yk. Okay, where k need not be same as n. So what we are saying essentially is that we have some sample space and we were mapping some probabilities, right? If this was event A, then this was PA, etc. And with every event, we were associating the random numbers also. So now you can think of this as some space of random numbers. And now what these G's are doing is taking it to a different space of Y's. This was X and this was Y. And it's possible that so all these X's were function of these events, right? A. So this event went to this one, maybe this one went to this one, maybe this was same as this. And now we are translating this space into a new one, Y space. So it's possible that this dot goes to this one goes to this one, and maybe this one also goes to the same one. Then if we ask the question that what is the probability that Y is this one, this green one, okay, this yellow one, and that same as probability of this plus probability of this. And for this, we need to go back to the sample space. So that is the probability of this event plus probability of event which gives rise to this X. So maybe it was this one, or maybe there were multiple ones which give the same X. Okay, so this is the idea. And there is a formula which essentially tells you the exact same thing, how to calculate the distribution for this new random variables. So we have the ones which are x1, x2 to x, and the new ones are y1, y2 up to yk, right? So where yj is some function gj of all the x's, x dot to xn. And natural question to ask is to find the joint distribution or joint probability mass function, assuming they are discrete, and that is given by this formula. So what we want is probability that y1 is some particular value, y2 is some other particular value, etc. Okay, and subscript would be y1, y2 all the way up to yk, and that is simply given as all possible sums of x1, x2 up to xk, sorry, xn, right? That would be in Rn. And if all of them satisfy that their functions give rise to this particular value, then we add their probability. So it's the probability that x1 is equal to x1, x2 is equal to x2, etc. Right? xn is equal to xn such that this g1 of x1, x2 up to xn gives y1, etc. Okay, so it's same as what we did earlier. So this is algebra, or in math language, this is visual representation. Okay, then we did some examples. For example, one natural case is sum of two random variables, right? So you are given x and y, and you want to find distribution of z, which is given by x plus y. This is something that we are always interested in. For example, if xi is binomial, so this is IID, then it would imply that z, which is sum over xi, is also binomial. Similarly, if xi were Poissonian, then z, which is again sum over xi, would also be Poissonian. So this week we discovered many such distributions in which you mix and match certain distributions to get the same distributions or different ones, but the known ones. All right. And then there was this grand theorem where if we have two functions, so z and w, both the functions of x and y. Okay. And if they are invertible, then we can write joint distribution function of z and w in terms of distribution of x and y. So g1 of zw, g2 of zw, where these are inverse functions, right? Same as what we did in 1D, and then we had to, if you remember, we had to multiply this dg inverse by dz. So here, instead of that, we multiply something called Jacobian, and this Jacobian matrix is given by, now it's 2 cross 2 matrix instead of just one number. So dx by dz. So x is inverse of z and w, right? So dx dz, dx dw, dy dz, and dy dw. So all these partial derivatives, we find this matrix, find its determinant. So this is the determinant, and that tells you how much stretch or compression there is in the space when you go from this xy space to zw space. Okay, so it's possible that x direction is stretched and y direction is compressed. So you have to take into account of all these different things. It's possible that it rotates also. Okay, so these rotating terms are given by these cross terms, and the diagonal terms are the stretching in x and y direction. All right. So I think we did some examples, but we are going to do some in the assignments as well. So, but we saw one important list of formulas. And that was when z is equal to x plus 5, we can readily find the distribution of z, which is just integral of distribution of xy with x and z minus x dx. And the idea is that you sum or integrate over all possible pairs such that their sum is equal to z. So when you add these two, you get z. So that is your distribution for z. All right. If it was x minus y, then you would do the same thing. If u is equal to x minus y, then fu of u, same thing. But now we have to make sure that whatever is inside this minus this, that should be equal to u. So how do you do that? You said this is u plus y, this is just u. So again, subtract this two, you get y. Okay, dy. Similarly, if v is xy, then fv of v, again, the product of numbers should be v, which means if this is x, then this has to be v here by factor of x. So that is the Jacobian term that will come here. So 1 by mod x here, and similarly if I divide by y, then I can write distribution of w, same thing, but now the ratio should be w. So if this is xw, this should be x, and there would be this Jacobian term. Right. So again, if you divide both this, you get w. You multiply both this, you get v. Okay. Then we saw something interesting, something called order statistics, which means distribution of minima or minimum value and second minimum, etc., all the way up to maximum. Right. So if we have some numbers x1, x2, all the way up to xn, I can rearrange them by x bracket 1, x bracket 2, etc., where this is our minimum value. So x1 is the least value, followed by x2, etc. Okay. And now we want to find distribution of these numbers. And there is this formula which is given, which is that fx1 up to xn of some numbers x1, x2 up to xn is given by n factorial times product of all these distribution functions. All right. 1 to n. If xi's are in ascending order, right? If they are not, then it's not possible to get these numbers because by definition they are in ascending orders. So if they are in ascending orders, we have this formula. If they are not in ascending orders, it's 0, right? And from that we can get marginal distributions also. And finally, we saw conditional distributions, which means probability that x is equal to some value given that the other random variable takes value y. Okay. So we can write that x is equal to x given that y is equal to y. So this we can write just like events, x is equal to x and y is equal to y, normalized by probability that y is equal to y. Okay. And in this is for discrete. For continuous, we would have function, distribution function. X. This is not x by y, but given. We should read it as x given y. So that would be f xy of x comma y divided by fy of y. So this is sort of a limiting case when things are continuous. So we can just normalize this thing by the marginal distribution of y. Okay. Any questions from this one? Okay. If not, then yeah, the final thing that we saw was random sums. So we can always define a random variable which is sum of some random variables, right? But how many? So why not make that also random variable? Okay, so that is the idea, that you call this as Zn, where xi's are IID of some distribution, but n is also from some distribution. So n is also a random variable. So it's a sum of some random variables, but how many? That also we don't know. That is also coming from some distribution. So this is called a random sum, and general formula would be that your f of z, this should be small one. It's the probability that z is less than or equal to z is sum of all possible values of probability that z is less than or equal to small z, given that total number is some n times the probability that n is equal to n. Okay, this is the general formula. This is total probability theorem. Our good old friend. So this is where we stopped. So any questions? Otherwise, we'll move to assignments. Okay, let's do the questions then. So this is the first question. We are given two distributions, x and y. Both are gamma distributed. First is gamma with parameters m and lambda, and the second one is with parameters n, which is different than n, but the same second parameter, which is lambda. They are independent, and we have to find the distribution of x plus y. So conceptually, it's very easy because we just saw the formula, but we have to work it out, and that is slightly convoluted. But we will do that. So let's do it, and you can do it in parallel with me. So we can call z as x plus y, and the distribution of z, as we saw, the formula is that xy, if this is if this is x, the first argument, then the second has to be z minus x. Why? Because the sum has to be z dx. And this in principle goes from minus infinity to infinity. Then I can break it down, minus infinity to infinity. These two are independent, right? It is given independent. So I can split it in terms of product of both of them. So this becomes fx of x, and then fx of z minus x dx. And fx is not equal to 0 for x greater than or equal to 0. So only when the argument is positive, I have non-zero value of integrand, which means our integration starts from 0. Also, this has to be greater than 0, right? Otherwise, this argument becomes negative, which means maximum I can go, the value of x is z. It becomes this one. And now we know that these are beta distributed. So the formula for beta distribution is this. So x is m comma lambda. Sorry, this would be y. Yeah. So the first one is I don't know why it's got stuck. Yeah. So fx of x is gamma distribution with parameter lambda and m. So it is lambda to the power m, then x to the power m minus 1 e raised to lambda x divided by gamma of m. This is the definition of gamma distribution. And similarly, the other one would be lambda to the power n. Instead of x, I have z minus x to the power n minus 1. This is e raised to minus lambda, and instead of x, again z minus x divided by gamma of n dx. Okay, now let's collect the terms. First, let's collect the terms which do not depend on x, then, because those can be taken out. Lambda raised to m and lambda raised to n. So that becomes lambda raised to m plus n divided by gamma n. And these two terms together, e raised to minus lambda x, and this is e raised to plus lambda x. So that gets cancelled, and only e raised to minus lambda z stays. So e raised to minus lambda z, and function of x is just x raised to m minus 1 z minus x raised to n minus 1 dx. Okay, this whole thing does not depend on x, so can be taken out. It becomes a lambda raised to n plus n e raised to minus lambda z gamma m gamma n, and now we have this east that is inside. And first, what we need to identify is that this is quite similar to beta integral. So beta of a comma b. Let me write a comma b. That is given as 0 to 1 x raised to a minus 1 and 1 minus x raised to b minus 1 dx. Okay, this is the general formula, and this we know. In fact, you can derive this. This is equal to gamma a gamma b divided by gamma of a plus b. Okay, so what I want here is 1 minus x kind of thing. So I can write x as z times u. Alright, so that this becomes 1 minus u, which means c minus x will become z into 1 minus u, and dx would become z du. So lambda raised to m plus n e raised to minus lambda z gamma m gamma n, and then this z can be taken out from the dx, and the limits are now 0 to 1, because when x is equal to z, u becomes 1, and x raised to m minus 1, that becomes z raised to m minus 1 and u raised to m minus 1, and this becomes z raised to n minus 1 times 1 minus u raised to n minus 1 du. Okay, and now these three terms add up to z raised to m plus n minus 1. And the rest of the terms are same. Gamma n. And this remaining integral is exactly the beta function, which can be written as gamma of n divided by gamma of m plus n. Now these are exactly cancelled, and this is by definition a gamma function. As you can see, something raised to m plus 1 e raised to minus lambda something sorry, this was m plus n minus n plus 1. So this becomes gamma of lambda, sorry, m plus n comma lambda. Okay, this is the exact form of gamma distribution, which means the correct answer is this one, the first one. All right. Now the second one. Now the rest ones are not as complicated as the other ones. Now we are given two random variables, x and y, continuous ones, and joint probability distribution is given. This thing, which is non-zero only in this region, when x and y both are in the first quadrant from 0 to 1. This is x and this is y. So only in this square it is non-zero. What we have to find is the value of k, the normalization constant. So how would we do that? What's the first step? Anyone? Okay, in this kind of questions, we just have to make sure that this function is normalized, which means the total probability should be 1, which means the integral, double integral from minus infinity to infinity of this function should be 1. Okay, but in our case, this is only from 0 to 1. So I can write 0 to 1, 0 to 1, and fxy is k into 3x plus 2y dx dy is equal to 1. Okay, so first I can take k outside, then this is integral 0 to 1 dy, and I can treat this as an integral of dx. Okay, which means that y can be treated as constant. So this becomes 3x square by 2 plus 2xy from 0 to 1. So I get k times 0 to 1 dy, and this value will be simply 3 by 2 plus 2 times this is y equal to that, sorry, x is equal to that. So when x is equal to 1, I get 2y. Now I have to integrate with respect to y. So this is just 3 by 2y plus y square from 0 to 1, which is k into 3 by 2 plus 1. And this whole thing should be equal to 1. Okay. This was equal to 1 all the way. Means k into this is 5 by 2 is equal to 1, which means k is equal to 2 by 5. That's the normalization constant, 2 by 5. Okay. For this value of k, we will actually satisfy the first rule of probability, that the total probability should be equal to 1. So that's the idea. Okay. The next one. Now we have two continuous random variables. Again, joint PDF is given, and it is non-zero in the first quadrant, meaning both x and y are positive. Otherwise, it's 0. And we have to find the probability that the first guy is greater than the second guy. So let's first visualize it pictorially. So in this region, it's positive, right? Or non-zero, the probability. And we have to find the probability that x is greater than y. Where would that region be? For that, we always look at the boundary case, which is when x is equal to y. That would be this line, right? X is equal to y. So we are either on the left side or right side. To find that, let's check something, some point on the x-axis. clearly x is positive and y is 0. So this point belongs to the region, which means it is this region. So this is the region where x is greater than or equal to y, or greater than y if we exclude the boundary. Okay. So we have to find probability in this region, which means we have to find the integral of this function inside this area. How do we do that? We take slices and integrate, right? So if I fix my x somewhere here, then my y goes from 0 to y is equal to x, because that's the upper boundary. Okay, which means our answer is integral of f xy, where my x would go from 0 to infinity, but for each x, y will go from 0 to x, right? Dx, dy. Once you do that, the rest of it is just mechanical, just algebra. So x is equal to 0. This is y is equal to 0 to infinity. Fxy is 6 times. So 6 I can take outside. This becomes e raised to minus 2x and minus 3y. So I'll write like this. And the integral is first it is on y, then on x, right? The way we have written. So this is dy, and that integrated over x. So 0 to infinity. Now this is integral over y, which means this x can be treated as constant. So that comes out an integral of minus 3y. That is just e raised to minus 3y divided by minus 3. Okay. Dx. 6, 0 to infinity. E raised to minus 2x. And this will be e raised to minus infinity. That is 0. So 0 minus e raised to 0, which is 1. So 0 minus minus 1 by 3, which is just 1 by 3. Okay, dx. So this gets cancelled with 2. So we have 2, 0 to infinity minus 2x dx. Sorry, I made a mistake. Yeah, this upper boundary was till x. So this will be till x, which means this would be 1 by 3 and this would be 1 minus 3x. Okay. So again 3 gets cancelled. So that leaves 2 outside. But here I would have e raised to minus 2x minus e raised to minus 5x dx. Now I can use 0 to infinity because x goes from 0 to infinity. It's just that y, the value of y goes from 0 to x. Okay. Now this would turn out to be 1 by 2 and 1 by 5. Yeah. In general, 0 to infinity e raised to minus tx dx is 1 by t. Yeah. Just remember. It's a nice thing to just remember so that you don't have to do it every time. Of course, you can do it every time if you want to. So this is 2 into 3 by 10 or 3 by 5. Okay. So this entire region was of probability 1, but the region below this line, that is 60% probability. So more mass is concentrated here than here. Okay. So the correct answer is, of course, 3 by 5. Okay. If you have any questions, just ask me. Okay. Right away. Okay. The next one. Now we are given two independent random variables, but discrete ones. And these are binomial. Binomial with parameters 2 and 1 by 3 and 3 and 1 by 2. Okay. So in real sense, it would be like having two coins. So this one is unfair with probability of heads is equal to 1 by 3, and that is tossed twice, right? 2. And there is this other coin, the blue one, which is fair. So probability of heads is 1 by 2. Heads can be thought of as success, and that is thrown thrice. And what we are asked is that probability that x is equal to y, which means same number of heads appear on both the coins. So how can it happen? Well, it can either land heads 0 in the first case, or once or twice. In the other case, it could land on heads 0 times, once, twice, or thrice. But we need both of them to be equal. So either both of them are 0 or 1 or 2. Okay. So the answer is probability x is equal to y is that it sum over all possible values of k such that x is also k and y is also k. And we know that k can take value only 0, 1 and 2. Right? Why? Because you are throwing the first coin only twice. So at most you can get 2 heads. Okay. This we can calculate. So this is x and this is y. So when k is equal to 0, this is, let me do it systematically. So for the first case, we have 2. So 2ck. Then the heads, which is the success probability, 1 by 3 raised to k, and 2 by 3 raised to 2 minus k. This is the binomial probability, right? And for the other one, again, it is 3ck, but with 1 by 2 raised to k and 1 by 2 raised to 3 minus k. K is equal to 0 to 2. So when k is equal to 0, I have to just expand. We can't do much here. This becomes 2c0 into 2 raised to k is 0, which means 2 raised to 2 divided by 3 raised to 2. And then 3c0. This is always 1 by 2 cube. And when k is equal to 1, so 2c1, 2 raised to 1 divided by 3 square, and 3c1, 1 by 2 cube. Plus when k is equal to 2, we get 2 raised to 0 divided by 3 square, and 3c2, 1 by 2 cube. Okay. This is equal to, the first one is 2 times 4 times 3 divided by 3 square into 2 cube, plus this, sorry, this is just 1, right? 2c0 is 1. And 2c1 is 2 times 2 times 3 divided by 3 square into 2 cube, and plus this one, 2c2 is 1, 2 raised to 0 is also 1, 3c2 is 3 divided by 3 square and 2 cube. Sorry, this would also be 1, right? This is 3c0, this is 2c0. So all in all, I can take out this 3 square into 2 cube common. I have 4 plus 12, that is 16, plus 3, 19. This is 19 divided by 3 square is 9 times 8, 72. It's ugly, but it is whatever it is. Okay. And 18 for the 72, right? Yeah, which means this is slightly greater than 1 by 4. 19 by 72. Yeah, the calculation is ugly, but I hope you get the concept, right? You want x and y to be equal, so it could be equal to any number k, which is possible. So only possible possibilities are 0, 1, and 2. Okay. The fifth one, this is very easy. So a random variable is given with mass function, which means it is discrete. So probability of my x being -2 is this, -1 is this, 0 is this, 1 is this, and 2 is this. And then we define y as x square. And what is the probability that y is greater than half? Okay. So our x can take 5 values, -2, -1, 0, 1, and 2. So correspondingly, y is equal to x square. So -2 would give 4, this would give 1, this would give 0, this would give 1, and this is 2. So these are possible values of y, right? Possible y's. And what we are asked is that what is the probability that y is greater than half? So as you can see, y is almost always greater than half. Only time it's not greater than half is when it is 0. So we can write this as 1 minus probability that y is equal to 0. Because that's the only time it's not greater than half. Now if the only time y becomes 0 is when x is equal to 0, because only 0 takes you to 0, right? If we were asked probability that y is equal to 1, then we had to add both these cases. But for 0, I have only one cases, which is 0. And what is the probability of 0? X being 0, that is 1 by 5. Which means the answer is 4 over 5, 80%. Okay, very simple. I don't really know why it is asked this week. Maybe they want to mix all the concepts so that we have always have the broad picture in our mind. Okay, now something about order statistics. So we have again two random variables which follow exponential distribution. Both are IID, by the way. And z is the maximum of x and y. And we have to find the distribution of z, capital F. Okay. So what is the by definition? Fz of z is the probability that z is less than or equal to z, some small z. Okay. Now, if I say that, let's say, A is maximum of B and C, that means that A is less than or equal to B, and sorry, yeah, for maximum we have to do it. A is greater than or equal to B, and A is greater than or equal to C, right? Only then A could be maximum of these two. In fact, even if we are given that A is greater than or equal to maximum of B and C, it means it is greater than both of them, right? Individually. So now the probability that Z is less than or equal to Z means that we have X also less than or equal to Z and Y also less than or equal to Z. Only then the maximum of X and Y would be less than or equal to C, right? It's the same thing, but I've written ulta. So our A is Z and these two are X and Y. Okay. So, and because they are independent, I can write probability that X is less than or equal to Z times probability Y is less than or equal to Z. Okay. Now probability that X is less than or equal to Z, that is just integral of this distribution of X from -infinity to Z, right? Because we want maximum value to be z. This is minus infinity to z e raised to minus lambda x dx. Sorry, there was lambda here also, right? So this becomes e raised to minus lambda x, and this lambda gets cancelled. So just minus this from minus infinity to z, which gives us e raised to minus lambda z. Did I make any mistake? Sorry, this should start from 0 because exponential is only defined from 0. Yeah. So this becomes 1 minus lambda c. Okay. Which means our fz of z would be 1 minus e raised to minus lambda z. And now what's the probability that y is also less than or equal to z? But both of them follow the same distribution. The answer is same, 1 minus e raised to minus lambda z. If we club them together, it's just a square of this thing, right? So that is the answer. 1 minus e raised to minus lambda z whole raised to power 2. Okay. I hope it is clear. Just remember this one thing. Whenever the maximum is asked, you write it like in this form, that fz of z is probability that x is also less than z and y is also less than z, and that is just product of this distribution functions, right? Okay. Again, similar thing is given. Now x and y are IID random variables with some distribution 3x square when x is between 0 and 1. And what is asked is the distribution, or rather the PDF of z, where z is minimum of xy. So minimum and maximum are slightly different. So we have z is equal to minimum of xy, which means if we want to find the distribution, cumulative distribution of z, that is till z is less than or equal to z, but we don't know if z is minimum of xy. Let me use different variables. C is minimum of AB. It means C is less than or equal to A and C is less than or equal to B. Okay. So another way around, A is greater than or equal to C and B is also greater than or equal to C. So these are our random variables X and Y. So what I should write is 1 minus probability of Z greater than or equal to Z. This means that probability that X is also greater than or equal to Z and Y is also greater than or equal to Z. And this I can break it down because they are independent, times probability that Y is greater than or equal to Z. And I know that both of them would be equal because they are IID. So I just have to find this quantity. Probability that X is greater than or equal to Z, that is simply given by integral of this from z to 1, because maximum it can take is 1. 3x squared dx, which is x cube from z to 1. So 1 minus z cube, assuming that z is between 0 and 1, right? So this is the answer. So this becomes 1 minus c cube r square, right? Because the other thing is also c. Okay. Now I want to find the PDF of this, which is just the derivative of what we found. It is just d by dz of same thing. So it becomes minus 2 times 1 minus z cube, and then derivative of minus z cube, which is minus 3 z square. So 6 z square 1 minus z cube. That is our answer, the PDF. This one. 6z square 1 minus z cube. And of course, z has to be between 0 and 1. Right? So I hope it is clear. Otherwise, please do ask me. Okay. Let's move on to the next one. This is very interesting. I mean, intuitively, it's quite clear. So, in fact, let me go to the ninth one first to get the intuition. It's the same thing. So, there are people entering an elevator, a lift, and on average, a person weighs 100 kilogram, slightly higher than the actual number, I guess. But okay, so the person weighs 100 kilogram on average, and there are some n number of people entering, but n is not fixed, right? Sometimes there are higher, sometimes they are lower. That follows some binomial distribution with mean 5. So on average, 5 people enter the lift with weight 100 kg. So on average, how much would be the weight that is borne by the lift? Okay, so that would be just naively what you expect is that there are 5 people on average, and each one weighs 100 kg on average. This average we intuitively understand they should multiply to give answer 500 kg. Okay, and that is in fact the correct answer. How is it? For that, let's look at the eighth question, which is exactly asking the same thing but more formally. So we have xi's, some IIDs, and all of them have same mean mu. So these xi's are the weights, and the mean was 100 kg, right? And n number of people or random variables are being added, and we have to find the expectation of this quantity. Okay. So expectation of sum of xi, I is equal to 1 to n. First comment, if n is fixed, then by linearity of expectation, we know that I can take expectation inside the sum. So this becomes sum from I is equal to 1 to n, expectation of xi, which is sum I is equal to 1 to n times mu, which is just mu times n. Okay. So it's the average number or the expectation of xi multiplied by this number n. Okay. So if n is fixed, then expectation of n would be n, and expectation of x1 is whatever it is, just mu, right? And you, as you can see, any other option does not fit this pattern. So it has to be this one. But now let's see why it is exactly that one. So now if n is random variable, like what is given in the problem, then I can define first Zn. Yeah. Is sum from I is equal to 1 to n xi. Then what do we know about expectation of Zn, where n is fixed? Expectation of Zn we just calculated. It is n times mu, right? Or mu times n, where mu is expectation of xi, any xi. So let me call it just expectation of x1. But we know that now we define Zn, which is sum from 1 to capital N xi, Now we have to find expectation of Z capital N, which is nothing but sum over expectation of Z small n times the probability that N is equal to N, right? This is total probability. So given that n small n number of people come, I know the expectation, but then n itself has some probability. So I multiply those probability, then add together. Okay, where n is from 0 to infinity. N could be any random number. Okay, so now we know that expectation of z small n, that is n times mu, times probability of n is equal to n. This is sum over all. Now mu can be taken outside. So this is mu into sum over n times probability of n. N is equal to n. Okay. This is nothing but expectation of n, right? This is not a factorial. Just exclamation mark. Which means this is mu into expectation of n. And mu was nothing but expectation of x1 or x2 or any of your favorite x, because all of them are ID. So the final answer is expectation of x1 into expectation of n, the last one. Okay. And now we know why this happens, right? Expectation of n was given to be 5 and expectation of x1 was 100. So we just plug these numbers in this formula and we get the answer. Okay, so this is the last one. Let's do it, and then if you have any questions, you can ask me. So we are given two random variables, again independent ones. Both of them are Poisson, but with different parameters, lambda1 and lambda2. And we have to find conditional distribution of x, given that x plus y is equal to n. Okay. So what we are asked is probability of distribution of x, given that x plus y is equal to n. This would be x given, sorry, some small x given n. This is given by probability that x is equal to x and x plus y is equal to capital N, sorry, small n, divided by this probability, which is x plus y is equal to n. And we know that if x is Poissonian of lambda 1 and y is Poissonian of lambda 2, then sum of these two, x plus y, that is also Poissonian distribution with the parameter lambda 1 plus lambda 2. Okay, the reproducibility criterion. So this we can use it here. So now probability x given x plus y is equal to n, x given n is probability that, again I can, this means that if x is equal to x, that means that y has to be n minus x, right? So let me first write it that way. Probability that x is equal to x with x, and probability that y is equal to n minus x, divided by probability that x plus y is equal to n. Now the first one is Poissonian with lambda parameter, so e raised to minus lambda 1, and then lambda 1 is to x divided by x factorial. This is the Poissonian distribution. Similarly, the second one is e raised to minus lambda 2 raised to n minus x divided by n minus x factorial divide by, because this follows, the denominator also follows Poissonian with lambda 1 plus lambda 2. I can use the same formula, e raised to minus lambda 1 plus lambda 2, and then lambda 1 plus lambda 2 raised to n divided by n factorial. Now some things very nicely cancel out. These things, e raised to minus lambda 1 and e raised to minus lambda 2. That gives this one. And then this lambda 1 raised to x and lambda 2 raised to n minus x. And on the bottom I have lambda 1 plus lambda 2 raised to n, that I can divide it into two parts. Lambda 1 plus lambda 2 raised to x and lambda 1 plus lambda 2 raised to n minus x. When they multiply, they give me this lambda 1 plus lambda 2 raised to just n. Okay. And outside, I have this n factorial divided by x factorial n minus x factorial. This we immediately recognize, right? Our good old friend ncx. This is lambda 1 by lambda 1 plus lambda 2 raised to x. And this is lambda 2, or I can write 1 by 1 minus lambda 1 by lambda 1 plus lambda 2 raised to n minus x. Okay, which is nothing but binomial with parameter n and lambda 1 by lambda 1 plus lambda 2. Okay, so this is interesting. The moral of the story is that when you add to Poissonian, the conditional distribution of x given the total becomes binomial. Okay, so this is how all of the distributions are intertwined. They are connected in some ways. This is one example where Poissonian is connected to binomial distribution. Okay, so the answer would be NCK lambda 1. Okay, I was calling it x, but they are calling it k. It is this one. Okay. So any questions? Anyone? Barsa, Swagatika, Dima. Any questions? Okay, I'm guessing not. Then let's meet next week. Same link, same time. Okay. Bye bye. Happy Holi.